Hello, my name is Margaret Harris, and I'm the industry editor at Physics World. I'd like to welcome you to today's webinar on Exploring Flatlands, Characterizing 2D Materials with Atomic Force Microscopy. The webinar will be presented by Professor Andras Kis of the EPFL in Switzerland, where he leads the Nanoscale Structures and Electronics group, and by Keith Jones of Oxford Instruments Asylum Research. During the webinar, Andras and Keith will be describing the latest advances in AFM technology and their implications for research on 2D materials, such as graphene. The speakers welcome your questions, which you can submit at any time during the webinar via the Questions tab on your screen. We'll have some time for them to answer questions at the end of the webinar, and any unanswered questions will receive a response by email after the webinar is over. You can also rate the webinar at any point using the ratings button on your screen. Now I'll hand over to Andras Kis and Keith Jones.
Hi. So I'll be starting this. My image just disappeared on my computer, but I will follow it with my copy of it. So what I'm going to talk about today is initially basic topography and some sort of advanced methods of topography that allow us to get accurate imaging. And the screen came back good. Okay, so I'll talk about tapping mode and LFM, and then I'll talk about some electrical techniques, including KPFM or surface potential imaging, Conductive AFM, SMIM, a little bit about some electrochemical stuff that was done over at Oak Ridge, and then coupled with that, they did some nanomechanics as well. All right, so let's start right off. At its base, AFM, atomic force microscopy, measures topography, right? That's the primary function of it. And so you would think that would be a very good use for this instrument on these 2D materials. But there are some requirements if you want to get accurate height data on these flakes and various materials. For one, you typically need a flat surface for a reference. If you're depositing these things on graphite or places where you don't have a real clean surface, you can run into some issues. We need something called censored Z. In other words, rather than relying on the nonlinear and hysteretic Z piezo that we use to measure these surfaces, we need a second look, something that's linear and accurate. Typically, on the Asylum instruments, we use LVDTs. They're basically coils of wire. They're very linear over a long period of wire, a long distance. Other people use different methods to censor their Z. And then finally, we need to avoid imaging in what we call mixed phase mode. Mixed mode phase imaging is not good. And I'll explain why here in a moment. So in order for you to understand sort of what this mixed mode phase imaging is, we go back to this Leonard-Jones potential, this idea as the tip and sample, as the tip approaches the sample. On the right-hand side, I'm away from the surface. As I get closer to the surface, you see a dip, that's potential well. That's what I'm going to be focusing on for most of this presentation, or for this part of the presentation. Right? And then this is, of course, energy. So we have a lower energy here, and then as we go up here, as we go up towards the peak, we have a higher energy. So if we take that and we zoom into the well part of that, we can describe this, and we look at the energy of this, and the energy is the total energy, is the kinetic energy, which is basically the probe, plus any potential energy of the sample. And I want to relate it to this. Graph that we often look at, this tune, the cantilever tune. Right? I mean, every time we take an AFM image, it's the first thing we look at, right? And so this is off resonance. On the left, it's off resonance. As we sweep through the frequency up to 74 kilohertz in the middle, we reach the resonance frequency and then we fall off. And we get this characteristic phase curve below it where you are in phase off resonance, below resonance, and you are out of phase by roughly 180 degrees above. Right? And we show this a lot. And what I'm going to try to relate to you is how this attractive and repulsive data, these shifts, what's the origin of these, and how can you use that to control and get accurate height data, right? So if we go to the next thing, so if we look at a repulsive field or repulsive force, we find that this well, this Leonard-Jones potential well, sharpens. If we look at an attractive force, it broadens. And this is kind of a simplification. In reality, you're actually getting a shift in the minimum of this. We're kind of showing the minimum not really shifting. Well, if the minimum didn't shift, we wouldn't be moving in or out of repulsive or attractive mode, right? But this shift is what leads to this, the shift is what leads to this repulsive and attractive shift in the resonance, right? And you can think of this, you'll see it in the next graph, but when this shifts, when this peak shifts, two things are happening. One, the phase shifts, but also the resonance frequency is moving out from underneath us, right? And what does that mean? As it moves out from underneath where we're operating, we lose amplitude. And so you're going to get a shift in that amplitude. The feedback is going to respond to that, right? And the last little bit on this slide is I'm going to bring in, and I'm just going to show you try to make it a little more clear where this is coming from. If we differentiate the energy curve with respect to this tip sample separation, we get the force, right? And so we can see here on the lower part of this curve, on this force, we've got a negative force, right? An attractive force. As we move up the curve past where the inflection point going is, I don't have a pointer, so I'm trying to describe it, we see an increase in the force to a repulsive force. We can imagine going back and forth across the x-axis on this, and that's our tapping. And so depending on where your tapping mode occurs, whether it's below that zero line or above that zero line, or if it's crossing that zero line. If it's crossing that zero line, that is mixed mode, and that's bad. And this slide that contains an image from, I believe, Garcia's paper, shows how, where we get this dislocation, I don't know what the best way, this sharp transition when you go from attractive to repulsive, and this is the source of your error. If we look at the upper left part of this graph, this is essentially tapping mode in AC mode. We call it AC mode. It belongs to history behind that one. But we look at repulsive mode, and you can see you get an accurate representation of that surface. The feedback, the Z piezo moving up and down, and then the Z sensor tracking that gives you an accurate map. You can also get very accurate maps in attractive mode, provided that there's not a really big difference in the charge on the raised part of that little graphic and the lower part of that graphic. As long as the charge is fairly uniform, you're going to get fairly accurate maps. Where you run into problems, where you're almost certainly going to run into problems, is when you've got mixed mode. And I've even seen inversions where high features actually end up looking like pits. So this is the key to getting accurate topographical images of your 2D materials. Okay? So moving on, we can also look at, so how to control the phase. So how do you do this, right? I always get ahead of myself on this one. How do we control this? Well, it's simple. You look at the phase just before you engage on the surface. You engage on the surface, phase goes up, you're in attractive. The phase goes down, you're in repulsive. If it's hopping back and forth, you're in mixed mode. Very simple, right? And how do you adjust it? You, in order to make that work, in order to get it into repulsive, you just hit the surface harder. So you start off with a bigger amplitude, and then you lower the set point down to 50%. If you can't get it in repulsive, raise the free amplitude again, and lower your set point down to 50%. 50% of your free air amplitude is roughly the maximum force that you'll get for any given free air amplitude. Okay, so here's some examples of some step heights that were done by our own Andras Kis. Right. So this is, if I recall, this is MOS grown on hydrogen sulfide. And so this is a giant triangle of this material, and then we're able to see an accurate step measurement. And on the lower graph, we're able to clearly see 5, 4, 3, and 2 layers. Okay. So then we can talk about the next method that's just a fairly basic AFM, again, just topography. But in this case, we're looking at lateral force microscopy. And in this case, it's real small now, the Xi group was able to see the actual lattice spacing of these guys by looking at the stick slip of the lateral signal. And they were able to measure very accurate lattice spacing in the two different directions. Another group was the Breton group at University of Nottingham, and they did a measurement where they were looking at moire patterns formed by lattice mismatch during epitaxial growth, the epitaxial growth of graphene. And I guess the key things to this paper were the fact that they were doing CVD growth rather than exfoliation. And they were matching some work that had been done by Woods. They were actually able to match the same periodicity of these moire patternings, right? And the moire patterning is when you put this graphene on the hexagonal boron nitride, you'll get a slight mismatch between the lattices, and that's what will form this moire patterning. We used to see that a lot when we did STM on graphite. You could see that, this sort of giant hexagonal pattern that you would get. What was interesting about this paper was they were able to see that in large regions of growth, in the middle, they had very little contrast and very little contrast in their moire imaging. But as they moved to the edges of these, both the number of defects and the spacing of this moire patterning tended to get worse and worse. And you can see on the right-hand side, it's really bad. Right at this crack, right? It's in the middle of the image marked K. And what they attribute that to is either a minimization of the energy of the strain from the lattice mismatch, or a region where two of these things grew together but didn't form, they didn't merge. So this was a really interesting paper using simple topography, right? And coming up with some really nice conclusions on a novel way of making these 2D materials. Okay, so then we can move on to sort of these electrical techniques. Kelvin probe microscopy. Again, it has many names: SKPM, surface potential imaging, KPFM. There are many ways of doing it. You can do frequency modulated, on resonance, off resonance. You can use a harmonic. You can use a second resonance. You can use amplitude modulated or frequency modulated. We have about 4 different ways that we can do it on the Asylum instruments. But the bottom line is that you're matching the potential of the tip to the surface. And if we look at this rather overcomplicated diagram, the key things to look at, or where it says DAC, digital analog converter, that DAC, in other words, the voltage, is being applied directly to the chip of the cantilever and therefore being applied to the tip. And if you look down to the left of that, we have a potential feedback loop that looks at the oscillations of the probe due to the potential mismatch between the tip and the sample, and we feed back on that until those oscillations go away. And again, there's many ways that we can do it, but the bottom line is we're matching the tip potential to the sample potential. Okay? So let's take a look at the next one. And here's the key, and I've seen a lot of different papers about what's the best resolution, what's the best way to get frequency modulation gives you better resolution, or amplitude modulation gets you better resolution. The bottom line is that the best way to improve your resolution is to keep in mind the tip sample separation. When you're tapping, when you do the main, especially if you're doing like a NAP technique, when you do the main scan, you're actually above the surface by your amplitude set point. And when I say amplitude set point, I mean the physical amplitude. That voltage that you're looking at on your instrument is actually a real distance. Typically 75, it can be anywhere from 20 to 75 nanometers per volt. Well, that means, and we measure it on the Asylum instruments by the actual sort of physics amplitude, where it's half of the peak to peak. What that means, though, is that when you stop and you apply the bias, and that AC bias, and then you're canceling it, you're actually above the surface by that amplitude. So you actually have to lower it. So we talk about lift mode or nap mode or whatever. The bottom line is that that's actually, you're starting out above the surface. So you typically need to use negative lift modes. And let me show you where this comes from. This was some work done by, this paper I think was Li Wei Chen, and I believe he was in the Bruce group when he did this. I can't read that, it's too small. So what this is this simple model that they use to represent the cantilever. And if we take it and we sort of look at the pink part, that's the cantilever. The green part is the tip apex, and the blue is the cone. And the key thing to understand, you got different tip radiuses and all that, but the bottom line is that when you're out at the right is away from the surface, and to the left is towards the surface. When you look at the contribution from the different ones, the dotted line is all three summed together. You see that 60, 70, 80 nanometers, it's almost equally coming from the probe the apex, or the probe apex, the cone, and the cantilever. But as you get down to 20, 30 nanometers, the tip starts to dominate. And let me show you sort of an example of that. This is a sample. That's the bottom line. Keep the tip sample separation as small as possible. And this was just a, I believe it was an electrode. Or it might have been, it doesn't matter. It's a thin film sample. There's a difference in potential between one side and the other, right? And what I did was I started from the bottom, and as I went towards the top, I was lowering the delta height to see what the resolution effects on the surface potential were. And what we found was that we had anywhere from you can measure this 1.5, 2 microns, something like that for that step. But as we move further up, we found that the resolution dropped to roughly 500 nanometers. Right? And that's all simple. And look at the resolution of all the little bits and pieces on that, right? That's a much higher resolution. I think that's probably corrosion or contamination on the surface. But this is a key thing. So no matter what method you're doing, and this applies to frequency modulated, amplitude modulated, off resonant. Right? Whenever I do amplitude resonant or amplitude modulated off resonance, I usually run about 5 kilohertz or so. I make sure that I'm in attractive mode, and I make sure that my free amplitude is really small as I can make it. If I can get away with 10, 15 nanometers, that means that the probe spends as much time as possible close to the surface. It's the surface I'm trying to measure, not the field above it. Right? I want to measure the surface. And so it doesn't matter what technique you're doing, try to get that tip as close to the surface as possible. Okay, so looking at the next one. Wait, yeah, okay, so this is just an example of this. I cannot read that, unfortunately, but it looks like Rack. Okay, I won't try to say their name. You can read it. For some reason, it's real small on my screen. All right, so in this case, what they did was they imaged this device. They built this device. It's a tungsten selenide device. And they put a source and a drain on it. You can see on the left. But then they actually induced defects using selenium. And then they went back and measured it during surface potential. And from the resolution on this, I'm guessing that they did, in fact, get quite close to the surface because this looks to be quite good resolution. So it's a nice application of surface potential. Okay. So then let's talk about conductive AFM. Conductive AFM is fairly simple. You look at the bottom left, you see you are biasing your sample. You're basically pushing current through your probe. Transimpedance amplifier, very simple. Look at the bottom right, you'll see it says V out equals I in times R gain. So I can tune this to whatever gain value I want. We at Asylum, we have a dual conductive AFM, we call it a dual gain stage, where we take that voltage out and we amplify it another 1,000 times to get a larger dynamic range. I think we end up with about 6 or 7 orders of magnitude. Okay? And so a nice example of that is molybdenum disulfide on ITO, and the point of this study was to look at the dependence of photocurrent on the numbers of layers and the wavelength of illumination. And this was a really neat study where they actually show that there is, in fact, a dependence, a very clear dependence on both the wavelength and the number of layers. It's a nice, clean use of this. This is also, because of this illumination, and I don't recall which instrument this is put on, we recently introduced the Infinity, and I just got mine in my lab, where we can actually take a fiber. The original one was installed with Frank Hamrijo down in Colombia. But ours is actually, I have a copy of his, and we can actually run a fiber from the bottom, whatever wavelength, whatever fiber you want. It just accepts the fiber. So it makes this kind of work a little bit easier. Sorry for the plug. It's required. All right, so then we also have a technique called scanning microwave impedance microscopy, or SMIM. This was developed out of the Sheng group, ZX Sheng group in Stanford, and was developed by this little startup called Prime Nano. It's quite an interesting technique. And what we do here is we actually send microwaves down to the surface at 3 gigahertz, and we look at the reflected signal. You can model it basically as a capacitor and a resistance. And what we get back is the conductivity and the permittivity of that sample. Very quickly through this one, because I'm running out of time, I'm sort of comparing it here with traditional scanning capacitance microscopy. And I'll give you the short version of it. Basically, FCM looks at just the magnitude, right? There is phase in there, but you're not really getting, you can't separate the resistance from the capacitance. Whereas with this newer technique, it also means that you can't look at metals and insulators. With this newer technique, we're actually looking at the X and Y output. We can then shift that output so that we match on a purely capacitive sample one of those two outputs to the capacitance. That means the other one must be resistance, right? And it also means when we modulate that we can look at DR dV and DC dV separately, right? And so that would be like microwave loss and then doping, whether it's the magnitude of the doping or the type of doping. And then on top of that, we are sensitive to metals and insulators. I did a composite metal that I got some real nice results seeing the different conductivities. Okay? And because we have a coaxial probe, it's higher resolution. So this is just a quick example of some stuff we did. I can't give you any details on the sample, but here's a device. Here was some topography taken. And here we can see a difference in the doping level between the center of the device and the source and drain. And then we could also clearly see a difference in the phase, which means it's doping tight. And we get a pretty good contrast in that. So it's very clear data, very nice data on 2D materials when you're trying to identify where your source and drain are and where your gate is. And then another quick example we did on properties of this graphene. So we were able to see 3 different levels of graphene, and we were able to see a difference in the capacitive or the capacitance data on those 3 levels. I apologize for the line being in a different part. When I made the section, apparently I made the section in the lower one shorter than the one on the right, but the green lines match up to the different layers. Okay? And so the final thing, apologize for going over, Andras. I'll go very quickly. We do this thing, contact resonance. This work was actually done at Oak Ridge National Lab. I'll give you the short version of this. Contact resonance, or DART, or Sprite, if you're looking at Donna Hurley's original work for this, is you put the cantilever on the surface, you measure the contact resonance, and you look for shifts. Shifts in that contact resonance tell you differences in the elastic properties of that surface. Right? You can look at, basically, in this case, stiffness. You can also get some loss information. Right? And so this work that was done, this is just an example. This is our little device showing the resonance. This work was done, and I apologize, somehow it got stripped in the process. This work was done by Nina Balka at Oak Ridge National Laboratory, Sergei Kalinin's group. I apologize sincerely, Nina, for it not being on the actual slide. I don't know if it can be put on later, but at least I said it. And we've got the open contact potential, or the open circuit potential. And then what they've done here is they've actually done this in the electrochemical cell. So they're doing both contact resonance and electrochemistry at the same time. And at the open circuit potentials, there's not any lithium injected into this surface. On the right-hand side, they're actually injecting lithium in, and they're able to see the change in the elastic properties of the surface. In other words, this is stiffer. So the material is stiffer where they've injected the electrodes, or the lithium. Okay? And so now, thank you for listening, and I'll sign off to Andras.
Thank you, Keith. Thank you very much. I also learned quite a lot of things. So I'll be talking about, I'll present several case studies, case examples of how we used atomic force microscopy, and it's a Sapphire model to answer some important questions about 2D materials. And when I say 2D materials, then I really mean the main material family that my group studies. They're the transition metal Dichalcogenides, which are actually let's say the next 2D material family after graphene and boron nitride to be studied. So now today we have maybe 30, 40 2D materials which are being studied, and there are actually literally thousands of more 2D materials to be discovered. So we focus mostly on the semiconducting ones in our group, and I will today be only showing examples on molybdenum disulfide, which happens to be the most robust, so we can do a lot of long studies in AFM without worrying about things like degradation and oxidation, etc. And towards the end, I'm also going to show some results on graphene ribbons, monolayer and bilayer graphene. So to connect with Keith's presentation, I'm going to first show an example of how we used Kelvin probe microscopy as easy to use electrical methods to answer some interesting questions about CVD grown molybdenum disulfide. So in the upper left corner you have a schematic drawing of now pretty much standard way of growing molybdenum disulfide in a CVD furnace. So you have a tube heated to something like 700 degrees centigrade. You flow an inert gas through the tube, and you co-evaporate sulfur and molybdenum oxide close to a substrate. Now, depending on the substrate, the choice of the substrate actually is very important if you want to get very high quality materials. So the most often used substrate is silicon dioxide, simply because it's easy to get it, it's very cheap. But unfortunately, silicon dioxide has a very high surface roughness, so the surface is such that you get hills and valleys which have a distance that can correspond to the thickness of your 2D film. And the surface is also amorphous. So to get better quality material than what you could normally get with silicon dioxide, we decided to use Sapphire instead. And on the bottom left picture, you have an optical image of a film that you get when you grow MOS2 on Sapphire, and you see that you basically get these triangles. So every triangle is a single crystal of molybdenum disulfide, and they merge together into a film. And on the right-hand side, you have an optical image of a sapphire chip, and in the middle, this yellowish film is actually monolayer MOS2, which is fully continuous. So it doesn't have holes like in the optical image on the lower left side. So now the interesting thing is, if you look at the edges of these triangles, you see that most of them seem to be constrained to multiples of 60 degrees. And the reason for this is that sapphire and MOS2, they are commensurate. So the lattice structures are such that you can get fit 3 unit cells of MOS2 onto 2 unit cells of sapphire, and you get a strong van der Waals interaction between the substrate and the film. And this van der Waals interaction then guides the growth, so that your film locks into only nice, the regular orientation, 0 and 60 degrees. And sometimes you can get also 90 degrees. So you can see this in, for example, close to where this says sapphire, and there's an arrow. Just above the arrow, there's a 90-degree oriented MOS2 single crystal. So now the important thing for this is to start with a very nice sapphire surface. So on the left-hand side, you have an AFM topography image of a wafer that you would normally buy. So this is already a very high-quality wafer, and it looks very smooth. So on the bottom, you have a histogram, which is constructed from the topography image. And then you get the standard deviation, which is 154 picometers, which is the same as the surface roughness, and it's already a very good number. So silicon dioxide, for example, would be somewhere around 300 picometers. So that would be, it would appear quite rougher. But now if you go through a step of annealing, then you get a nice surface reconstruction. So you get these very nice steps, which are atomically smooth. So now if you do the same exercise and you do take a histogram after you've properly leveled the image so that the steps are horizontal, then you get a surface roughness of 33 picometers, more or less, which is pretty close to the actual noise floor of the AFM. So these are now real atomically smooth surfaces, and you need to do this to reveal the surface atoms so that the MOS2, when it grows on top, can actually lock into the surface lattice on the bottom. So now the next thing for us was to see, when we have our film, to actually see if the fact that we have this very nicely oriented single crystal grains in the film, that whether this has an influence on the electrical properties. So we were hoping to see that this indeed is very good for the electrical properties of the film. And then to answer whether this is really the case, we used scanning Kelvin probe microscopy. So Keith very nicely presented it, and we applied it to a field effect transistor. So we built a field effect transistor, like on the bottom left image, which contains 2 grains in a certain orientation of MOS2 with electrical contacts. Those are the yellow lines. And then we could load this into the AFM and connect all the electrodes. And then on the electrical scheme, basically we use a voltage source. We use one of the channels on the AFM controller as the voltage source to bias the device, get the current flowing through it. And then with the gate electrode, so that would was just connected to the substrate, and again we used one of the channels on the output of the controller, we could modulate the conductivity, so make the channel more or less conductive. And then with the AFM tip, doing the Kelvin probe microscopy, we basically use the AFM tip as a local voltage probe without actually touching the channel, and we get an image which corresponds to the local voltage drop plus with a contribution from the work function difference between the tip and the material, of course. But now on the right-hand side, you have an example of a Kelvin probe image. So you can see on the left and the right side, you have the two electrodes, so they appear homogeneous, and there's a big potential difference between them. And then you have this object in the middle are the two single crystals of MOS2, and you see that they appear with more or less homogeneous colors, except that you have in the middle this discontinuity. And then if you look at the line plot, you can see how much this discontinuity represents in the potential drop. What you basically have here is a grain boundary. So these two grains have a non-highly symmetric misorientation, so they are misoriented by 92 degrees. And you get, in that case, a grain boundary which contains a lot of voids, and these voids lead to extra electrical resistance, which then manifests itself as a large voltage drop across these two grains. So that's the discontinuity in the middle. And then if you look at how much this voltage drop actually corresponds to in terms of length of extra material, so you basically get as much voltage drop over this one grain boundary, which is maybe less than a few nanometers across, as you would get over 4 microns of semiconducting material. So in effect, every grain boundary would increase the length of your material. So if you take a lot of material with a lot of these grain boundaries, then actually it would, from the electrical point of view, it would appear to be much, much longer and more resistive than what it would be without these grain boundaries. So now when we saw that this method actually works pretty well, we used it to our the kind of highly symmetric lattice orientation, relative orientations that we got in our grown film. So this is an example where you have two grains. So on the uppermost image is the schematic of the relative orientation of the two grains, and then in the middle you have the Kelvin probe image, and on the bottom you have a potential scan line across the channel. So this is a case for the 0 degree misorientation, and in this case, theoretically, it's possible to get a seamless joint between the two grains, and you're not actually expected to see any kind of electrical resistance appearing if that's the case. And really, if you look at the potential line scan, you see that you don't really see any kind of discontinuity like on the previous slide. So it's all seems to be pretty much within the noise limits. And interestingly, we got the same thing if you look at two other cases that we see in our film. So this is the 60-degree misorientation in the middle, where you basically have the two lattices in the opposite orientations, and the single crystals are joining together. And in this case, you're supposed to get a mirror twin grain boundary, which looks as if you took the lattice and then you removed one line of either sulfur or molybdenum atoms, and then you joined them together. So this kind of lattice, this kind of a grain boundary, even though it's there, it doesn't introduce any extra electrical resistance either. And the same case is for the misorientation of 30 degrees. So all these three in the Kelvin probe do not show discontinuities, which means that they don't introduce any extra electrical resistance. And then if you make a large area device out of this film, and you measure its two-contact electrical mobility. So this is an example of such a device that we made. You have an optical image on the bottom, and between the first and the last contact, labeled 1 and 6, you have something like 80 microns of distance, and we expect to see maybe 15 to 20 grain boundaries. And then if you look at the mobility, it doesn't decrease as you increase the channel length, so it stays pretty much constant, which is another indicator that you don't have extra electrical resistance coming from scattering from grain boundaries. So that's as far as Kelvin probe microscopy goes. Now, in the remainder of my talk presentation, I'm going to be talking about using the AFM for studying different aspects of the mechanical properties of 2D materials, starting with molybdenum disulfide membranes. So for a lot of studies, it's quite important to get the material off the substrate using some kind of a transfer method, and also to maybe locally suspend it so that you don't influence the electrical or the optical properties of the material with dangling bonds on the substrates or maybe defects in the insulating film, like in the silicon dioxide. And this is an early example of what we did in this direction. So we made some films of exfoliated first MOS2 using the adhesive tape technique, and then we transferred it onto a silicon nitride membrane into which holes have been etched using electron beam lithography and reactive ion etching. And then this kind of film we could image on TEM with high resolution. But then more importantly, in the context of this talk, we were able to also do mechanical measurements on this kind of suspended membranes. So we basically used the AFM probe to locally deform the suspended part of the MOS2 film, and on the bottom you will see an example of an AFM image of a suspended membrane, and then we use the AFM probe to deform the middle, and we measure the force and the deflection in the same time as normally done using force distance curves, and then at the point of breaking we retract the AFM probe and then we image again the film, and then you can see very nicely here in the middle the hole that we made in the film. But also more interestingly, this hole seems to indicate the fact that there are no larger tears that would extend along the membranes. It seems to indicate that the material fails as a brittle material, so in the similar way as silicon or glass would shatter when you deform them a lot. Now, from the force distance curves, which look like these on the right-hand side, using a model from one of the hardcore mechanics and the membrane books, we could actually measure the deformation force, the breaking strength, and the Young's modulus of the 2D film. And we were able to do this on a single layer film. So you see on the bottom you have a red and the black curve are the measurements for a single layer film up to the point of breaking, and on the blue line you have the same thing for the bilayer film. And from this we saw that MOS2 had a Young's modulus of around 280 gigapascals, which is similar to the Young's modulus of stainless steel. And also more importantly that we can have a breaking, so the strength at breaking or the strain at breaking is 11%, which means that you can actually apply quite a lot of strain to these materials to be able to, for example, integrate them into either flexible substrates, or you could maybe also use this strain to modulate the basic physical properties. So the fact that you can apply such large strains has actually prompted a lot of theory groups to calculate what would be the effect of such large strains on quantities such as band gap or electrical, heat conductivity, etc. in this class of materials. And they found very early on that you could have a very strong modulation of the band gap. So by applying strains, you could actually start shrinking the band gap, and you could even fully close it at around the breaking strains in this material. So there were a lot of optical studies that looked at this, and we decided to look at this from the point of view of electrical measurements. So we used again atomic force microscope to perform electromechanical measurements where we combined mechanical measurements and mechanical straining using the atomic force microscope together with electrical measurements to be able to extract some more useful information on the physical behavior of 2D materials. So on the top left side you have a scanning electron microscope image of a device with a suspended MOS2 membrane. So you have the 3 contacts. So this basically just to have 2 devices in one go. So we can break more of them during the AFM imaging. And in the middle part, there's a suspended MOS2 membrane, and then with the contacts, we can bias again the membrane, and we can look at the electrical conductivity. So on the bottom left-hand image, you have the schematic of the experiment. So the MOS2 membrane is suspended above a trench in silicon dioxide, and then we have the source and the drain electrodes. And again, we use one of the output channels of the AFM controller to apply the bias voltage (VDS) to the membrane so that it conducts current. And then on the drain electrode, we connect externally a current to voltage converter, a small IV converter. You can buy a lot of these different models on the market, and then the output of the converter is connected to one of the input channels on the controller, and in this way we can synchronize the measurements of the current with the measurements of the force and the deflection as we're deforming the MOS2 membrane in the AFM. So then on the right-hand side you see the two graphs. So on the bottom side you have the classical force distance curve. You have the tip deflection versus scanner extension, where you can basically recognize when the tip starts to deform mechanically the ribbon. And then also from the shape of the ribbon, shape of the membrane, we can basically say that the membrane is being nicely deformed, that you don't have a slippage of the tip, that we're not hitting the bottom of the trench and things like this. And furthermore, that there is no real hysteresis in the deformation part, so that there is no material being pulled out from under the electrodes, for example. So now on the top side, you have the current, which is recorded in the same time. So it's a bit noisy, but the current levels are very low, so they're on the picoampere range. And the reason for this is that we didn't dope we didn't apply a gate voltage, because we were worried that by applying a gate voltage to the membrane, basically all the effects we would be seeing would not be intrinsic, but coming from the fact that you're changing the distance between the membrane and the gate, so that you're changing just the strength of the electrostatic coupling. So now you see that in the same time as the membrane is being deformed, we see an increase of the current, and this increase of the current then means that you have a decrease of the resistance, and this decrease, so sorry, I had in the original, I had an actual formula. So if you go in the paper, you will see that this decrease of the electrical resistance or the increase of the conductivity can be modeled using, there's a mod formula which basically models the conductivity at the band edge of a slightly defective semiconductor, which is what we have in the case of MOS2, and you basically get a conductivity which depends exponentially on the band gap and ratio of the band gap to the temperature multiplied by the Boltzmann constant. So basically, by measuring the electrical conductivity, we can, and its change with the deformation, we can measure the change of the transport band, or change of the band gap with the deformation of the material. So now the complication is that the strain that we apply is non-uniform, so it's concentrated mostly under the tip of the AFM probe. So we had to model the strain distribution using finite element modeling, and if you do this, you basically get a family of curves like in the following graph, where you can model the total to-contact resistance as a function of the contact resistance, and as a function of different rates of change of the band gap as a function of strain. So then you get these families of curves. Now the idea is that you go to your actual mechanical measurements, and then you pick the curve from this family from the simulations, which has the lowest sum of squares. So basically, you're doing a fitting of the curves to the measurement results. And then when we do this, we basically get, in a monolayer case, we get a strain rate of -73 MeV per percentage of strain. So the band gap is decreasing. In the case of bilayer, we get a bigger number, because in this case, you also have the effect of two layers getting closer to each other, so this coupling is increasing, and you can also do some funny things with the band structure when this happens. And in the tri-layer case, we get the smallest rate of change. And then when we express these numbers, so when we then actually go back to how much the band gap in the case of this deformed film was changing, we can construct this kind of color plots where the biggest rate of change and the band gap was in the middle of the suspended part, and it would correspond in this case of a tri-layer to something like 130 millielectron volts. And then it sharply decays as you move further away from the point where you deform the ribbon with the membrane with the AFM tip. And then if you calculate the gauge factor, we basically get these numbers from mono, bi, and tri-layer MOS2, and the gauge factor in the case of bilayer is actually quite good and comparable to what you would have in silicon or standard semiconductors, which you could normally use as a macroscopic strain gauge. Now, we also did this, initially this experiment was historically we were first trying to do this experiment not with MOS2 but with graphene, and to be honest, the real motivation for this was to see if the application of a mechanical strain would lead to opening of band gap in graphene. So there were some theoretical predictions back in the days when I was starting my lab, which indicated that this could be the case, and by applying strain you could solve the problem that graphene doesn't have a band gap. So we spent a lot of time implementing this this geometry and this measurement technique, and to be short, we didn't see a band gap opening, but we saw something else that could be interesting. So this is again the very same geometry. We have suspended this time a ribbon, because the idea was that if you have a ribbon, then you might be a little bit closer due to confinement to the actual opening of the band gap. And then we again deform it with an AFM tip. We apply voltage, we measure the current. The notable difference is that in this case we used very small AC voltages, because we were looking at very small hypothetical band gaps, and then we used an external lock-in to lock into the oscillation frequency of the applied voltage signal, and then again the lock-in output was routed to one of the inputs of the controller. It's a bit more complicated setup, but again pretty much the same thing. So we were able to deform and measure the conductivity in the same time. And these are the examples of measurements on a single layer graphene. So we see again a deflection, which force goes up, and in this case, actually the tendency is opposite. If you look at the current seems to go down. So the resistance goes up. So there is no. This is actually not still an indication of the band gap opening, because this could be also explained by the reduction of the Fermi velocity as you apply strain. And on the right-hand side, we have the change of resistance for different ribbons, different widths, and we basically saw a lot of variation. In some cases, we even saw a negative gauge factor, but the gauge factors here are around 10. So compared to MOS2, which is a semiconductor, this is much less, because graphene is a good conductor. But then in the case of bilayer, we saw a very interesting effect. So we could see in a number of devices that we made this kind of behavior, where we have on different colors, different deformation experiments performed on the same device, one after the other. And we could see in this resistance some kind of oscillations, which seem to be actually quite reproducible as you go from one deflection run to the other. And then eventually, in a collaboration with the theory group, we were able to explain this in terms of rippling in a two-layer ribbon. So when you have this two-layer ribbon and you apply strain, then one of the mechanisms with which strain can relax is the formation of this kind of a local ripple or bubble, where the top layer gets decoupled from the bottom, and then as you increase the strain, then the size of this decoupled region increases, or maybe their number also increases. And then the idea was that these two films will basically act as you will have current flowing through both of them, and if you increase the size of this decoupling, then the relative path difference will change, and you get something like an interferometric effect. So basically, whenever you have you can have positive and negative interference between the currents flowing on the two ribbons, and then with this we could basically reproduce the same type of resistance oscillations that we saw in the experiment. So at this point, I would like to wrap up and thank my group and the hard work and the results that they made. So I can show you here, and also the funding agencies which supported the work, and also the collaborators that helped us model these results. So I guess we can now maybe take over with the questions.
Yes, thank you, Andras and Keith, for great presentations. We'll now take a look at some of the questions that have been sent in. So one of the questions, and I think this is for Keith, is when KPFM is done on a 2D material, do the results depend on which substrate it's lying on, and if so, how?
Yeah, so that's an interesting question. It really depends on, initially, sort of to first order, it depends on how it's mounted. If you're growing these materials on a substrate and that substrate is effectively floating, or you're your 2D material is floating on top of that substrate, then yes, you're going to get a big offset due to that material. If, however, you're mounting it like Andras did, where he's putting these electrodes in, and he has complete control over the film itself, right? Not the film, the material itself, then in that case, it's not going to directly affect it. But I want to point something out, and that is that there can be secondary effects, because if you remember the paper on that I talked about from Beaton's group, and I apologize, that was done in tapping mode. I had it in the wrong order. It looked like that was done in lateral mode, but that was actually in tapping mode. But if you look at those, you notice that you get mismatch of the 2D material with the substrate. I can almost guarantee you that if you did a surface potential map of those materials, there would be a difference in the potential from the center to the outside, and it would correlate to the strain relief that they were hinting at. So the secondary effects, yes.
Okay. So we had a few questions, actually, of people requesting copies of the slides. And if you do want a copy of the slides, please go ahead and ask for it by using the question tab, and then you'll receive a copy by email. That will let me asking a question via the question tab will tell us who you are, so we can contact you afterwards. Okay, next question. What is the best metrology technique to characterize the defects in 2D materials such as graphene?
So I can probably take that on. So that's, I would say priority-wise, probably the best would be STM, because you have a better shot at seeing the individual pieces. Then I would say probably second would be lateral. You saw those really nice results from the work that was done that I showed. And then finally, there's something we've done recently at Asylum, and that is we'll put these materials in fluid. Obviously, you have to be a compatible fluid, and we will use that fluid to screen the surface charge that normally messes up your small amplitude tapping. And we use like a 2 angstrom tapping amplitude, and we're actually able to see atomic defects. So that technique shows promise. We've done that a lot with calcium. What is it? I can't even remember. I do it a million times that I can't remember. But we do it with various materials. We've got a bunch of them in our brochures and stuff. But yeah, so I would say in that order: STM, lateral, and then small amplitude tapping in fluid. Do you have a comment on that one, Andras?
Yeah, I agree. So I came once to Asylum to look at some of these samples with in a liquid, and it seems to be working quite well. Okay.
So another question about it's kind of a related question. A question about how to reduce the noise if you're in tapping mode.
Okay, I can probably do that one. I'm an instrument guy. So I would say the priority to that would be the environment. The very top thing is you got to get your instrument in a quiet environment, or you have to design the instrument to ignore the environment, right? And so the first step to that is location. Put it in a basement in a deep, dark castle in Europe, and you're probably going to get low noise. Isolation, acoustic isolation. So you need to isolate the mechanical path between the probe and the sample. Acoustic isolation will get there. So you got to use a hood. You got to use something to cover it up. And then finally, I would say active cancellation for seismic. So something like one of these table stables that the Swiss company makes. Their distributor here is Herzan, but I forget, JRS, I think, JRS. They're really good. Those are the ones we use. I prefer their AVI series, but those guys do a really good job of isolating acoustic. And of course, there's passive. Some instruments do real well with just bungees or something like that. And then on top of that, once you've gotten past that, then you start to move to the instrument itself. And what we find is that having a short lever, so having small spots and a short lever, reduces the thermal noise and therefore gives you better imaging. And then on the instrument itself, designing to avoid noise, in other words, making all the active resonances in the system above your operating bandwidth, and then using a modulated laser source helps as well. And I don't know if Andras had anything to add on that one.
No, nothing really.
Okay.
Okay. Next question. Getting a lot of instrument questions.
Yeah, they look like that.
To reduce the tip and sample distance, it's not only the amplitude and the set point that are affected. The K of the probe also contributes to that. Could you comment on that? And this person adds that also in the repulsive mode, tip wearing can also play a role. And the question is how you can reduce tip wearing.
We did a lot of studying of this early on when Jason and Roger first started doing this attractive, repulsive stuff and started taking advantage of it. I'll give you the bottom line first, and then I'll tell you a little bit of subtle stuff. A higher Q on a probe, in other words, a higher quality factor, a sharper peak, means that it's going to be easier to image in attractive mode. A higher Springs constant is going to make it easier and repulsive, and the reverse of those is true. So spring constant effectively makes it easier or harder to get into repulsive. The second part of that, where we talked about wear, we found that wear in either repulsive mode or attractive mode is fairly low. Attractive is a little bit better. Mixed mode is where you kill your tip, right? And the reason for that is that sudden shift in the amplitude when it switches back and forth. And to look at this in a more subtle way, if you recall that slide where I had both the Leonard-Jones potential and then I had the force overlaid on it. And so when you're thinking about this conceptually, think about moving laterally along the x-axis as changing your amplitude and your set point, and moving up and down along that axis, but you have to stay on the curve now, moving up and down as changing your spring constant, right? If you make your oscillations larger, then you have a bigger line on that graph. If you make your oscillations smaller, you basically a smaller line drawn on that graph. And so that's sort of two ways to look at that, either conceptually or practically.
Okay, getting loads of questions here. I should note that if your question if we don't get time to answer your question, don't worry. We did receive it, and we'll be contacted by email with an answer. Got time for a few more though before we wrap up today. Question is, to what extent should we check or consider the effect of tip specifications on the resolution of AFM, regardless of the method we choose to use?
So, I'm sorry, could you say that one again?
Yeah, sure. It's to what extent should we check or consider the effect of tip specifications on the resolution of AFM, regardless of the method used?
Can I answer that one, Andras? Is that okay?
Yeah, go ahead.
Okay. So on very, very flat samples, the tip radius is not that important, not as important as you would think it is, because there's always one piece of that tip that sticks down farther than anything else. Where you run into problems is if you have a very rough sample. If you have a very rough sample, you could be running into some problems with you have to get as sharp a tip as possible. I know IBM used to make these fib tips. I think they still do. And Nanosensors has these SSS tips, I think, that are super sharp. And Olympus has some as well. So, yeah, if your sample is rough, it's extremely important. If your sample is smooth and flat, like a lot of these 2D materials, then you can often get around that. Okay, and a question about bias. How do you bring bias to samples when you're measuring operating transistors using KPFM? Use bounding or probe tips? Seems a lot of questions about probe tips.
Yeah, so I guess that's for me. So we use the wire bonding to very small chips, something like 20-pin chips, and that was what we initially did. But then we had some problems in fixing that into the AFM. So using some standard chip sockets, so we didn't have enough space to reach the entire chip. And now we actually just take a silicon chip, and when we make a device, we put the contacts on the edge, and then we use little pogo pins. So we have some kind of we machine some little holder with pogo pins that contact those pads.
Okay. So that is, I'm afraid we're running out of time here. So thank you to everyone who asked a question, and thank you all for listening to the webinar. If you'd like to watch this webinar again, particularly if you had some problems with buffering or connection problems, it will soon be available at connect.physicsworld.com/webinars. So have a look there, and please recommend it also to your colleagues who maybe weren't able to listen on the day. Thank you again to our speakers, to Keith and to Andras, and thank you to everyone who's joined us today. This webinar is now finished.